Hello boys and girls, ladies and gents, this is Miss Chikoi coming to you with another video from the dark inside a tiny room and a whiteboard that's actually a shower board, but it works. So we're going over series and parallel today, so more on circuits, but we're going to go a little more depth, a little more rigorous than we have done before. So I have some definitions that, if you're here taking notes, you can go ahead and write down, but we are going to explain each one in turn. So let's first again re-clarify what do we mean by series and parallel. And I ordered these incorrectly. It should be not parallel and series, but series and parallel. But so this is a series circuit. So remember, a series circuit is when they come in one line, one after another, whereas the parallel is two different lines, two separate paths. And so you can often think of it as an and an or. So series is it hits this resistor and then it hits this resistor. A parallel is it could hit this resistor or it could go another path and hit this resistor. And so remember my little squiggles, all they mean is some sort of resistor. It could be a light bulb, which is just a fancy resistor that also lights up. So we're first going to look at the voltage. So we're going to imagine we have a 10-volt battery, which they exist somewhere. They're not super common. And so we can kind of see, and by the end of this, I hope we can explain why we have our two parallels light bulbs, which are much, much brighter than if we, say, had our two series light bulbs. And they're hooked up to the same batteries. They're hooked up to the same light bulbs, but they are not hooked up in the same manner. So we can see how these are in parallel. So they form, just like on our circuit board, two parallel lines, where these form one line in a row. And so we'll kind of go over why that happens, what that means. So to start off, if I have a 9-volt battery, or excuse me, 10 volts, we're going to use some nice numbers here, 10 volts, that means my electron leaves home 10 volts in its pocket. So every electron that comes from this battery leaves home with 10 volts in its pocket because it's a 10-volt battery. So to get through this resistor, the electron has to spend some energy. You can think of your resistors like speed bumps in the path of your electron. So it has to spend some energy to get through this. So for argument's sake, let's say that it has to lose 4 volts, spend 4 volts of energy to get through here. So if we take 10 and subtract 4, now we have a 6-volt electron because it already spent 4 volts here. We also call that, you'll see that written as a voltage drop. By the time your electron gets home, it should have 0 volts. It should be done. Because the idea is it has all this potential energy to start with. By the time it gets to the ground, just like when we have potential energy, by the time we have an object get to the ground, it has 0 potential energy. By the time we have our electron get to ground, we should have 0 energy as well. So that means if this one took 4 volts, if I had 10 and then I lost 4, and so I have 6 left, and later I'm going to have 0, that one loses 6 volts. And so that's what I mean by in series, the voltage is split. We have some original voltage of the battery, and the resistors split it, normally unevenly, unless they're exactly the same, and then they'll split them evenly. So don't assume that they are going to be even. And so we can actually even use this to predict the size of the resistor, which we'll get into a little later. Parallel is different. So remember here, our 10 volt had to spend some volts here, and it had to spend some volts here. So it had to add up to 10. For our parallel, I'm short, forgive me. For my parallel, however, if I have a 10-volt electron, it doesn't have to hit each one of these. If it goes down this way and comes back home with 0 volts, that means it only hit one resistor. That means that one resistor took all 10 volts. Same thing if we have another electron who went a different direction and comes home with 0 volts. This one also lost 10 volts. So you'll notice these have the exact same voltage, and because they're hooked up in parallel directly to the battery, it's the same voltage as the battery. So that's what I mean by the voltage in parallel is the same. These are always going to have the same voltage as each other because, in formal words, the potential difference on either side of these is the same. So they're going to be the same. So we're now going to look at the current. So looking at the current, again, I'll just redraw a series. And so remember, the current is how the flow goes, so how much flow we have going through. So we're not going to worry as much the voltage here, so we're talking about the current. So let's say our current, so remember current is written with an I. You can still see that. Current is written with an I. And so let's say we have a current of 2 amps. So we have 2 amps. So if 2 amps is a measure of how many electrons are flowing through that at a particular time. So we could say that's 2 electrons per second. That's not actually what 2 amp means, but we'll, non-rigorous. So if I have 2 amp electrons leave home, 2 amps of electrons return home. So you're going to have the same current throughout the entire time. And so that's what I mean by in series, the current's all the same because it's all the same path. It's one lane of traffic, one road. There's no other roads you can take. You're going to have the same amount of cars that enters, the same amount of cars that exit, hypothetically that no one died. In parallel, this is not true because we don't only have one path, we have 2 paths. So if we have 2 amps leave home, we could have, I'm going to do 3 amps because it's going to make my numbers easier. So if I have 3 amps leave home, we could say 2 of them go this way and 1 of them go this way. So just the way that my loss of 4 and 6 added up to 10, my split of 2 and 1 will add up to 3. And then they come back together and we have one big river again. That's going to be 3 amps. So that's what I mean by in parallel, the current splits. We have 3 to start with, but they go separate routes, so the total current will split. And last but not least, talking about the total resistance. So if we do the total resistance of them, so let's say this is a 4 ohm resistor and a 6 ohm resistor. Remember, ohms is just a measure of the resistance. Then my total resistance, because these are in series, is the sum of the individuals. So the total resistance, so I'll write that as resistance R, T-O-T, total, is equal to 10 because it's just 4 plus 6. For our parallel, I'm not going to expect you to do the math on this. I will show it really quick, but I'm not going to expect you to be able to do the math. But I do expect you guys to understand that the total resistance will always be less than any one of them. So if I have a 4 ohm resistor, we'll keep it the same resistors as here, a 4 and a 6. These are not going to add up to 10 because if I have more paths, there's less resistance. It's like if you have more lanes in a freeway, it's easier for traffic to flow. You'll notice that very quickly if some lane of the traffic goes down and the traffic is very bad very quickly. So when these are in parallel, we're actually going to have less resistance. And so you add them as fractions, or you add the inverse. So basically that'd be 1 over 1/4 plus 1/6, which 2/12, 3/12, 5/12, over 5, 2.4. So the total resistance in this one is 2.4. So again, I don't expect you to be able to do the math. I did want to prove that it worked, but the total resistance here is 2.4 ohms, or 12/5. So anytime you have resistors in parallel, they actually decrease the total resistance, because every time you add a new path, you make it easier for electrons to flow. And I'm going to go back and erase at the top so we can do a little bit of V. All right, so if we have a series and a parallel, we know that by increasing the number of paths, we've decreased the resistance. So in parallel circuits in general, because they have decreased resistance, they're going to have increased current. Series, again, if they have the same individual resistors, is going to have the opposite. They're going to have more individual resistance and less total current. And so if we make up some numbers and add them here, so let's have two 10-volt batteries. And let's have resistors of 4 ohms and 6 ohms. We already said that the total resistance of this is going to be 10 ohms because we add them. The total resistance of this is going to be less than any individual resistor. And when we calculate it out, we get 2.4 ohms. And if they have the same voltage, we can use our little voltage, current, resistance triangle to help us solve this. So if we are solving, so let's say we want to solve for the total current here, what you want to do with your triangle is cover the thing you're trying to solve for. So I'm trying to solve for the current, so I'm going to cover I for my current. And so that means I have to divide V over R. So I'd get my voltage, which is 10 volts, over 2.4 ohms. And we get our 10 volts over 10 ohms. So hopefully 10 over 10 should be pretty easy math. It should be 1 amp. 10 volts divided by 2.4 is... we do 10 volts divided by 2.4, we get 4 point...
Yeah, 4 point... Oof. 1.666.
0.16?
17. Round.
2. So we get about 4.2 if we round. So we can see very clearly that this is a lot more current than we got, even though we had the exact same resistors and the same battery. So that is one of the reasons why when we have our parallels, as we do, and our series are much dimmer than our parallel. Let me plug my parallel in here really quick. And so we can see pretty clearly that my parallels are much brighter than my series for this reason. The other reason has to do with the voltage. So that's the reason why, because there's more current, and if there's more current, if you've ever looked at a river or anything of flowing water, the more current there is, the more flow, the more energy, right? It's the difference between having a waterfall, a large stream fall on your head, or that, bucket of Gatorade they do at the Super Bowl, and someone pouring like a little cup of water on your head. You're going to feel a very different response from that. The other one to consider is the voltage. So we could go back, and if I know the current, I could solve for the voltage. So the easy thing is for my parallel, well, each one of these is going to get 10 volts. Because we already said voltage is going to be the same for our parallel resistors. For our series, we know it's going to split, but we may not know exactly how much. The way I picked my numbers, though, I do know, but we can still use the V equals IR. So they don't each get 10 volts, but our current is the same. So they do each get 1 amp. So we're now solving for the voltage of individual resistors so we can cover up our V. And that tells us that we should be multiplying the current times the individual resistor. So the current is a 1, which makes our math very simple. So 1 times 4 is 4, and 1 times 6 is 6. So these also get 4 and 6 volts. So they both have less current by quite a bit, and these have much more energy, much more voltage. So because they get more electrons, and those electrons have more energy, your things wired in parallel are going to be much, much brighter. You can also go back and figure out exactly how much current goes down each row by doing the same thing we did here, except we know the voltage, we know the resistance, and then you can do each individual one that way. And so similarly, this is going to be 10 divided by 4 and 10 divided by 6. So the current through these, I'll do this. It's going to have 1 amp of current. And then each one of these is going to have a separate current. Our total was 4.2 amps, but our current's not going to split equally. And so if you're an electron, would you rather go down a path of less resistance or more resistance? Hopefully, if you're thinking clearly, you'd rather go the path of less resistance, less traffic. And so that's what we're going to see here. We're going to have a much larger, and it's going to be, if I could do my math, 10 divided by 4, 2.5. So it's going to leave about 1.7. So we're going to have 2.5 amps go down the 4 ohm and 1.7 amps go down the 6 ohm, because they would more electrons are going to take the path of least resistance than the most resistance. Notice these amps are still more than the total we got over here, even though it's split because of the way it's hooked up. All right, hopefully this provided with you guys with some good ideas on how to wrap it up. Series is our and. It hits this one and it hits the other one. Because of that, each electron has to hit more than one resistor. And so that means the voltage that that electron carries is split. However, since it's an and, they're all in the same path, they're all going to get the same current because it's the same pathway, same river. And because, again, it's the same path, that total resistance is going to add up because it's just one after another. Parallel, because they are different paths, your electrons only have to spend their volts in one place. Because of that, your voltages are going to be the same. But because they are in different places, the current will be split because you have 2 paths. So your current will be split up. And because you have 2 paths, your total resistance is less than any individual resistor because you have multiple pathways to get there. All right, hopefully this was helpful. Good luck, and I will see you guys next time.